It does seem kind of dangerous that way, doesn't it, Mateo? Like, or you could just swim out there, even if the water's not going down the tube. Like, it's just still this massive, massive pipe that goes down. Like, what if somebody fell in? I don't know. Yeah, it doesn't seem super safe. Maybe that's why it's not very popular. You don't see it more often. It doesn't seem very safe. I'm sure it's roped off somehow, but still. All right, so what are we doing today? Confidence intervals. All right, we're going back to confidence intervals. But this time, instead of a proportion, we're doing a confidence interval for a mean, for an average. Okay? And so that means this is a one sample t interval for a population mean, a one sample t interval. So you got a video to watch. It's not super long this time. And then some online problems. I put online there. But that is for your weekend, right? You got lots of time. That's not due for you till Tuesday. Lots of time. It's not posted yet. I'll get it posted this afternoon. Hopefully that little bit of lost time isn't that big a deal since you have till Tuesday. I'll get it as soon as I can, though. So let's talk about this, all right? You ready? A one sample t interval for a population mean is what we are looking at here. So first off, remember these are t intervals instead of z intervals. We'll talk about why that is here in a second. But first, let's remember the general structure of a confidence interval. You take the statistic, which remember comes from a sample, right? The statistic is what you get from a sample. Then you add and subtract the margin of error. That's the general structure. Now, when we did this for proportions, what does that look like? Well, that was p hat plus or minus. So the margin of error was that critical value times the standard error. And for that case, the critical value, we called it z star. How many standard deviations do you have to go out to capture the desired confidence? So that was our confidence interval structure in the previous unit. The statistic plus or minus z star times the standard deviation. Well, this, for means, is going to look very similar. So instead of p hat, our statistic is x bar, right? It's an average instead of a proportion. Plus or minus the critical value times the standard error. Evelyn, you are correct there. Maybe put a squiggly equals. I don't know how to do that either. But the standard error is the estimation of the standard deviation. Okay? Now, all of this can be found, this might help answer your question as well, Evelyn. All of these can be found on the AP Statistics formula sheet, right? So you go to the formula sheet. I was going to come here anyways, so. So before, right here, was the formula we used for the standard error, right? The square root of p times q divided by n. The only difference between the standard error and the standard deviation was it's an estimate because we have to use p hat instead of the actual proportion, the population parameter, since you don't know the population parameter. So you do the best you can by using the sample. But yeah, they are basically the same idea. But we're not using this one, right? Because that was for proportions. We want it for means. So we got to scroll down. Here is the sampling distribution for means. And so our standard error right here is right there. Our standard error is the standard deviation S divided by the square root of n. Hopefully that formula looks familiar, right? We used this formula way back when for sampling distributions, because we've done sampling distributions for means before, way back in what, January? So we're going to start using that formula again a little bit. And so to do this full confidence interval, it'll be x bar plus or minus. Now here's what the video was talking about. Hopefully you saw that. Our critical value is no longer z star. Z star didn't quite work, okay? It is t star times the standard error. And so the video was about how to find t star, etc. Now, I want to go into more depth. Why t star? Why is it not a z star? Z star seems like it should work. And up until about 1905, that's what we used. There is such a thing as a one sample z interval for a population mean. There is such a thing as that. But it doesn't quite work in many circumstances. It doesn't actually capture the confidence that you want when you set it at a certain level. And that wasn't known until this dude by the name of William Gosset. Why do they keep adding more? Because we got 26 of them. All right, we want to be inclusive. We want to be inclusive. It's not just all about your ex, all right? That joke never gets old. So, story time. You ready for a story? I'm ready for a story. William Gosset. All right, let's talk about William Gosset for a second. William Gosset was the lead tester, beer tester for the company Guinness. Hashtag life goals, am I right? He was the lead beer tester for Guinness around the turn of the 20th century. Okay? And he used one sample Z intervals. He would test the beer. All right? He would test the beer. He would test the taste, the hops, and the chemical makeup of everything. He would test it. And then he would take the batch. He would do his hypothesis test. And he would either reject it or fail to reject it to see if it met the standards of the company. And so he would do this. Now, he had to use small sample sizes, okay? He couldn't do huge sample sizes because he wanted to live, and you can't just sample that much beer and live, among other things. But, well, he would reject a sample of beer. He would reject a batch. And then occasionally they would take that batch to another facility and test it more thoroughly, okay? Because it's more expensive to test really thoroughly, so they wouldn't do it that often, but they would sometimes test it more thoroughly. And he realized, they were starting to see like, whoa, you're rejecting way too many batches. Like some of these batches that you are rejecting were actually good. Like it wasn't accurate. His Z interval wasn't accurate enough. And he's like, why the heck is this happening? Like the math is good. Why is it happening? Well, Guinness paid him to go get a stats degree. Either they paid for it or they let him go do it. He gets he studies stats, gets a graduate degree, everything. He studies stats, And he figures out that Z star doesn't quite work. So one of the things he does is he runs a simulation before computers, mind you, before computers. So his simulation is this. He gets 3,000 pieces of paper, all right? That's going to be his population. And he gets, the data he uses apparently is the heights of inmates. Okay, so he goes to a jail or something, or all the jails around, and he gets the heights of inmates. He puts each inmate's height on a card. All right, that's his population. And then he starts sampling from this deck of cards, this 3,000 deck of cards. And he takes small samples, like 2, 3, or 4. He finds the average, he finds the standard deviation, and he plots his sampling distribution, puts a dot. Then shuffles it all together again, takes another random sample, finds the average, finds the standard deviation, plots another point on his sampling distribution. He does this hundreds and hundreds of times so that he actually builds by hand a sampling distribution. And he finds it's not normal. Close to normal, but not normal. It's a little bit different. And it's different depending on how big of a sample he takes. So this is what's called the T distribution. All right, it's close to a normal, but a little bit different. Okay? So here's the T distribution and what it looks like for different samples. So if you have 1 degree of freedom, the red here, the red one is the T distribution. The blue one is the normal. As you can see, they're pretty different. So that would be for a sample size of 2. If you took a sample size of 2, very small sample, they're very different. Well, then you take a sample size of 3, which gives you 2 degrees of freedom. And so the red one right here, the red one is for your 2 degrees of freedom. The green one is the previous. The green is the previous, the red is the current, and the blue is the normal. As you can see, with 2 degrees of freedom, it got closer to becoming normal. And then 3 degrees of freedom, it got even closer to being to the normal. Here's 5 degrees of freedom, even closer. 10 degrees of freedom, you almost can't tell the difference, right? Where's the red one? I don't know. I'm colorblind. 30 degrees of freedom. 30 degrees of freedom. You almost can't tell the difference between the red and the blue. It is almost normal. Somebody was asking me a couple of days, I forget who was asking me. If you're here, holler at me. But they're like, Bull, hey, I'm doing a t-test right now. Or I think it was for AP Bio or something. They were doing a t-test. Like, why does my chart not go above 99 degrees of freedom? Why can't I go above that? Like, does it not go above 99? Well, because 99 degrees of freedom, there's almost no difference between the T distribution and the normal. They're very, very close. Okay, so that's probably why many tables don't go beyond that. The Z interval and the T interval would be almost identical with sample sizes that large. Now, to make it easy though, like when do I use T, when do I use Z? Nah, we have calculators, all right? We're just always going to use T, okay? There's no reason to switch between a Z and a T, nah. We're always gonna use the T, okay? If it's a confidence interval for a mean, we're gonna use T. Michelle, correct. Yeah, the more degrees of freedom, the more normal the model would be. Yep. And you see above 30, man, it's almost, at least visually here, indistinguishable. Very similar. So if Gossett was doing his beer samples with sample sizes of 30, he probably never would have seen a difference. And we wouldn't even have the t distribution if he was doing large. But of course, he would have died because he's taking 30 samples of beer over and over again every day. And that will lead to an early grave. But instead, he was taking sample sizes of like 3 and 4. And as you can see, there is a difference between the normal model and the t distribution for smaller samples, which is why he saw the difference. Okay, that's a little story time. Hopefully that kind of was interesting, at least a little bit, which is why we have to use the t star instead of the z star for a confidence interval of means. All right, so let's do one. Hopefully this isn't you right now. Hopefully. Maybe not? No? Never. You would never, right? You will miss that about distance learning, I bet. You will miss that part. You know you've slept through a class. I've seen people do it. It's like, wait, class has been over for 5 minutes. Why are you still logged in? Nobody just stays logged in, drooling on your keyboard, I bet. So, let's do this. How much sleep do college students get? All right, how much sleep do college students get? To find out, you take a sample of 25 college students and find the sample average to be 6.64 hours with a standard deviation of 1.05. All right, we can do all that because this is quantitative data, right? We're asking them a number so we can find the average of a number. It's not categorical anymore. Create a 90% confidence interval for the true mean amount of sleep that college students get based off of this sample. Assume the conditions for inference have been met. So we're going to focus on just the calculations and not the 4-step procedure. But don't worry, the 4-step procedure is still there. State, plan, do, conclude, right? Got all those 4? We'll get there. But let's first just focus on the calculations. So our general form here will be x bar plus or minus t star times the standard error. So our average is 6.64. So for our interval, we're going to add it and subtract it, right, to get our 2 boundaries, plus or minus. All right, so we need a t star for a 90% confidence interval from a sample of 25. Those 2 things give me t star. So when we type this into the calculator, all right, remember where it is? It's essentially an inverse norm, but not for a normal model. It's for a t distribution. So it's an inverse t. Second distribution. Right underneath inverse norm is inverse t. All right, here are the 2 things it asks for. It asks for the area and the degrees of freedom. Those are the 2 things we need. So to figure those out, remember you think of the normal model. Well, it's a t distribution technically in this case. But with my bad drawings, you certainly can't tell the difference. If we want a 90% confidence interval, that means we want 90% in the middle. How much is in the tails? All right, so in this calculator computation, it is asking us to put in these areas, the tail areas, not the central. Okay, those of you who have the 84 are probably used to this, how it always does the left area. That's the area it's looking for, the area to the left. So how big is that right there? So if it's 90% in the middle, that means we have 5% in each tail. That's the number we're putting in. The degrees of freedom is n minus 1. So our degrees of freedom here are 24. So I'm going to plug those two things in, and that will give me my t-star. So area, 0.05. Degrees of freedom, 24. And then that will give me my t-star. Negative 1.71. Now that's the left boundary. They gave it to us as a negative because that's the left boundary. The right boundary would be positive 1.71. Just to give you the whole picture there. Doesn't really matter. I mean, we're going to add and subtract this number anyways, right? So whether it's positive or negative doesn't matter. Algebraically, we're going to add and subtract it. So 1.71 times the standard error. Can I explain what the purpose of the degrees of freedom are? So, the degrees of freedom, essentially in this case, kind of the sample size determines what this curve looks like, okay? The t-distribution looks different depending on the sample size, okay? Whereas the normal distribution looks the same on all of these. The normal distribution is the normal distribution is the normal distribution. But not so for the t-distribution, okay? The t-distribution will look different based off of what's called the degrees of freedom. Essentially, how big the sample size is, okay? And in this context, the degrees of freedom is n minus 1. It's not always going to be the case. Degrees of freedom. I know it's complicated. I'm not going to claim to understand it 100%. Okay? I'll try to give you a little bit of idea. The problem with degrees of freedom is you get two explanations. One explanation is this, and that's it. Which is not enough, right? You're like, okay, Bolt, give me more. Like, what else does it? Yeah, I'm with you. The other explanation is so crazy far over my head and over the head of this class and possibly the next stats class after that. It's useless to us. Like you Wikipedia this and you're like, all right, I get the first sentence and then nothing else. If you've Wikipedia'd anything, you know, especially math related, that's how it goes. Like you read the first couple of sentences on Wikipedia, you're like, all right, yeah, addition, blank plus blank. And then boom, wait, what? Abelian group, subgroup, and what is happening right now? Why is this an addition? It's kind of like that. There's no middle ground explanation that I've found that's great, but here's my attempt. Here's what a degree of freedom is. Say you have a sample of n equals 5. 5 numbers. And those 5 numbers have an average, oh, you can't see that. There we go. Have an average of, let's say, 20. All right, if you add up all those numbers, they equal 20. I'm going to pick the numbers now. The first number, I have the freedom to pick any number I want. 32. All right. I can still make the average 20, right? Could happen. Now I'm going to pick the second number. I have the freedom to pick any number I want. Third number. I have the freedom to pick anything I want. This third number could still be anything. The fourth number could still be anything. Keeping this true, keeping the average equal to 20. But now my fifth number does not have freedom. That fifth number cannot be any number it wants to be. If this over here is going to be true, if the average is going to be 20, this fifth number is locked into place now. It is locked into place. It cannot be anything. We could, I don't know what it actually has to be, whatever 32 plus 18 plus 21 plus 1 plus a number divided by 5 would equal 20. I don't know what it is. It's an algebra 1 problem. I'd rather not do it. But it does, that fifth number is locked in. It's not freedom. So this sample size of 5 only has 4 degrees of freedom. A sample size of 5 in that case only has 4 degrees of freedom. I hope that makes some sense. For us right now, it's always 1 less than the sample size. I hope that helps. I hope it helps. All right, let's finish up our confidence interval, okay? It's a good question. I'm glad we had the conversation. I hope it makes you at least feel better about this weird idea of degrees of freedom. So we have x bar 6.64 plus or minus 1.71 times the standard error. So the standard error is the standard deviation, 1.075 divided by the square root of the sample size, 25. Again, if you don't have that formula memorized, go to the AP Statistics formula sheet and you will find the standard error formula there. But we've used that in the past, right? We used that in Unit 5 when we did sampling distributions. Time to just plug this into the calculator. Let's do the margin of error first. 1.71 times 1.075 divided by the square root of 25. 0.36, let's go 8, 0.368. All right, so here is our, now this is actually sometimes a perfectly good way to report it, right? 6.64 plus or minus the margin of error. You can sometimes see a confidence interval reported that way. But we should also be able to report it as an interval with the lower and the upper, right? So now I'm just going to add and I'm going to subtract. Just like our quadratic formula days, right? Negative b plus or minus, all that good stuff. So 6.64 minus 0.368 and 6.64 plus 0.368. So there are my two boundaries for the confidence interval. 6.27 to 7.01, I guess, maybe. So we all know the sentence, right? I am 90% confident. The interval from 6.27 to 7.01 captures the true mean. All right, not proportion anymore, right? Not proportion. The true mean amount of sleep that college students get. All right, ladies and gents, ask me a question. Anything on that calculation not make sense? It is going to take some time getting used to not to say proportion, isn't it? Yeah, it's been ingrained in our minds for so long to say proportion. But yeah, we are talking about means now. So the true average sleep. Yeah. We'll get to we will do the 4-part process here in a bit. But it is the same. Like the same sentence frame is gonna work. I am 90% confident the interval from blankety blank to blankety blank captures the true average amount of sleep that college students get. Yeah. Hopefully the sentence structure is like riding a bike. Bolt, you know what happened last time I tried to ride a bike? I broke something. Well, brutal. But yeah, we will work on the 4-part structure for sure. All right, before we get there though, let's practice the calculations, okay? So, Khan Academy has a 4-question assignment there for you. It's always 4 questions, isn't it? I'm sure Khan has done like a statistical analysis on the precise number of questions for practice, like the best number of questions, and it came up with 4. Probably like 4.32, so it rounded down. So head on over there. Let's take maybe 15 minutes. Try those out. See if you can calculate a confidence interval. If you get stuck, please throw some questions in the chat. Be like, oh, wait, how did you do that again, Bolt? I will answer you. Let's see. Oh my Another minute or two, and then we will talk about some of those. I'll maybe pick one to go over, but keep going. Try to get at least a first attempt on everything. See how you're doing. I think it is definitely worthwhile to practice this. Again, if you got a specific question, throw it in the chat for me. Just a few more minutes. All right, ready to talk about one? Let's see. 3 and 4 went pretty well. 2, 8. Let's do number 2. I'm guessing number 1 score was a little bit lower just because it was number 1. Let's talk about number 2 real quick, shall we? Let's do that one. So, Camilla is curious about the average length of the female blue whales her organization monitors. She takes a random sample of 4 female blue whales from this population. Their average recorded length is 78 meters, and the standard deviation is 10. So that's from the sample, right? The distribution of lengths in the sample is roughly symmetric with no obvious outliers. Based on the sample, what is the 95% confidence interval? So we're going to take the 78, plus or minus. We first need the T-star. I'll do that down here, I guess. The T-star for this situation, right? So our degrees of freedom are equal to 1 less than the sample size. So it's just 4 female blue whales. So it's a very small sample size, so our degrees of freedom is 3. Now, what is the area going to be? Well, of course, we have our normal model here. Let's see, where can you see this? Over here. Up here, right? There you go. 95% is in the middle, which means our two tails are going to be 0.025. Right, 2.5% is 0.025. So I'm going to throw that into the calculator. Let's see, second distribution, inverse t. Inverse t right there. Right underneath the inverse norm, which we use for a z-star, right? So they're right next to each other. Area, 0.025. Degrees of freedom was 3. Negative 3.18. Negative 3.18. Is our degrees of freedom. So it'll be plus or minus 3.18. I guess the negative, I might take the negative away. That doesn't really matter. We're going to add and subtract it anyways, aren't we? Times the standard error. Our standard error will be 10 divided by the square root of 4. Oh, that's kind of easy. The square root of 4 is 2. 10 divided by 2 is 5. But I'm going to type it all into the calculator anyways. 3.18 times 10 divided by the square root of 4. So 15.9. Yeah, that's what good. That's 15.9. So that is 78 plus or minus 15.9. Let's see, they want the actual number, don't they? So I got to actually do that addition subtraction. 78 plus 15.9 and 78 minus 15.9. So 62 to 93. 62 to 93. Looks like I want B in this case. Looks like I want B. Questions there, anybody? All right, holler out if you think of one. Time for the easy way. You ready for the easy way? Because, of course, your calculator can do all of that for you. All right, your calculator can do all, you probably guessed that. Maybe you even found it. The calculator can do all of that for you, of course. So, hopefully you kind of know what to look for, right? As long as you know what it's called, you might be able to find it on your calculator. This is a one sample T interval. Can we find something that looks like that on the calculator? So I'm going to go stat, tests. That's where the Z intervals were, right? And for the proportions, same place. So I need to find a T interval. No. Those are all T test. There's a T test. We're going to use that one someday. That one looks pretty good. T interval, right? Doesn't that look pretty good? 2 samples. There's a 2 sampled T interval. That's going to be your video. We want this one, number 8, a T interval. On the Casio, hopefully you just go through the menu system. You want to go to an interval. You want a T interval. You want a 1 sample T interval. I'm hoping that it's pretty self-explanatory on the Casio for you. But I go to T interval. Now, when you first come here the first time ever, it's probably on the first one, data. It's probably right here. Because sometimes you will just type in the data into your calculator, and it can take all the averages and stuff from your data. They didn't give us data. They gave us the summary statistics. So come over here to stats and hit enter on that side. Not data, you want it to be the stats. Then the X bar is 9. Or no, so what is our average? Average is 78 for our blue whales. The standard deviation, she said, was 10. The sample size, N, was 4. And the confidence level was 95%. So we type it all in, and we're going to hit enter a bunch of times. Okay, so you want to be in stats, 78 for our average. We're just typing in S of X is the standard deviation for the sample, N, and the confidence level. Thinks for a while, and there we have it. 62.09, that rounds up, perfect. And 93.91, exact. So there you go. If you know what it's called, it's much easier to find. Hopefully that makes some sense there. For sure. I assume you mean for the calculator, Annie? All right, good deal, good deal. All right, so you go to stat, and then to tests. It's where all the hypothesis tests are, and the intervals are all in the same place for the 84. So if you remember, the 1 proportion z interval is also here. All that stuff is under tests. Then we got to find what we need, which is a 1 sample t interval. And the 84 just calls it a t interval. It doesn't put 1 sample there. Kind of wish it did, but it doesn't. The 1 sample is right there. And again, for your video, we're going to be using the next one down. There it says 2 sample t interval, but that's your video. 8 is the one we want, a t interval. Go over to stats at the top. And that way you can just plug in everything the problem gives you. The average, the standard deviation, the sample size. And so it will calculate the t-star, all that stuff for us, right? And then the confidence level. And then you hit calculate. Enter, 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 enter. And it gives it to you. Cool, cool. Yep, you can always use the calculator, all right? There's no like, you have to do this by hand, really, I don't think. You can always use the calculator. All right, a little bit more to do, a little bit more to talk about, but hopefully the calculation, actually finding the interval, makes some sense, okay? Now we got to fill in everything else. So the one thing I want to talk about here today, the last thing, are the conditions. Okay, the conditions. Most everything about this is going to be the same. The state part is going to be the same. You're going to say what you're going to do. Okay, we're going to do a 1 sample t interval for the mean. You're saying what you're going to do. That's kind of be the same. The plan part is, I think, the hard part. What about the conditions? When are we allowed to do a 1 sample t interval? So, thankfully, the 3 conditions are the same. First, the random condition. Same as always. Okay, you have to have a random sample. Then, the 10% condition. Just like always. Okay, we have to sample less than 10% of our population. That's also the same. No difference. The last one, the large counts. That one is a little bit different. Okay, we still have to do it. Like, we still need to have the large counts. But the way we do it is a little bit different. Because if you remember for proportions, it was always n times p, n times q greater than 10, right? Well, we don't have a proportion anymore. We can't do n times p. There's no p. So, what are we to do? Well, for large counts, there's 3 possibilities. You only need one of them, but there are 3 possibilities. Only one is necessary. Now, remember, let's take a trip back for a second. Do we know why we need the large counts? Ooh, I like that. All right, let's do this, ladies and gentlemen. In the chat, extra credit. First person who can tell me, why do we need the large counts? Oh, Maria, give me more than that. You can't just say vocab. What? You use the word it. That doesn't count. Oh, no, Michelle, you're getting colder. Not quite. Don't use the word it. You can't say it is normal. What is it? It. I know that you don't know, that nobody knows what it is. What is it? There it is. It's the sampling distribution. Ed's got it there. The sampling distribution needs to be normal. I kind of have to put everybody's together. You and your it. All right, there's our last one there. That is putting, Annie put it all together for us there. To make sure the sampling distribution is normal. Okay, that's the whole point of the large counts. There's 3 ways that can happen. 1, if the population is normal. Then the sampling distribution will also be normal, no matter what. Oh, I can't write. Sampling distribution is also normal. We actually already knew that. We studied that at the beginning of the semester when we did sampling distributions. So we knew that already. Now, sadly, we almost never get to use that one. All right, if we knew something about the population, we probably wouldn't have to do a confidence interval in the first place. So we rarely get to use that one, sadly. Okay, so how else can we do it if we don't know whether the population is normal anymore? Well, you also know the second way as well already. Does anybody want to know think they can guess what the second way is? Because you do know this. We did it in the first chapter of this semester. What was one of the other conditions for our sampling? Angel, yes. I'm going to yell at both of you, though. What's it? You and your pronouns. But yes, Angel, you are right. I'm guessing you know what it is. If the sample size n is greater than or equal to 30. If n is greater than or equal to 30, the sampling distribution will be normal. Equal is okay as well. Equal is okay. The last way is a little complicated, okay? If n is less than 30, we're not dead in the water. If n is less than 30, we need to look at the shape of the sample. Okay? If it's plausible that it came from a normal distribution, if it's plausible that it came from a normal distribution, then we continue. So if we make a dot plot of our sample and we're like, yeah, that could have come from a normal distribution, then we kind of assume number one is okay and we move on with our lives. Okay? Now, what does that look like? In short, it means no heavy skew. It is like an educated guess. All right? I don't have any evidence that it's not from a normal model. I'm going to go with it. No heavy skew and no outliers. Okay, and you're just kind of using a gut feeling here. There's no like, oh, well, this is the boundary. No. No boundary, no thing like that. Just gut feeling. You look at it and you make a decision. Okay? We're not trying to split hairs here. There's never going to be like, ooh, is that one kind of an outlier? Or is that too much skew? No, that's not the point here. Okay, that's not the point. It's got to be obvious. Okay? No heavy skew and no outliers. So let me just give you a few examples before I let you go. We are going to keep practicing this, but I do want to try to finish the thought before I let you go. So, it does require a picture. So you get your sample, you have the data, and you draw a picture of it. So that picture could be a histogram. All right, so here we've got ourselves a histogram. And, you know, it's symmetric. There's no heavy skew anywhere. There's no outliers. So, yeah, I believe it. It could have come from a normal model. Done. Move on. Met. All right, large counts is fine. It could come from a stem and leaf. Remember stem and leaves from way back in the day? It's been a while, hasn't it? Now, when you look at this one, though, do you see how we have a pretty heavy skew going on right here? New do to boot it. Right? That's a heavy skew. Yeah, I don't think that came from a normal. Not met. Okay, I see a heavy skew. Nah, can't go on. Done. Does not meet the conditions. Okay. It could be from a box plot. Now, this one actually has a very slight skew to it. It is kind of stretched to the right a little bit. Yeah, but it's not a heavy skew. All right, it's not super, that could still have come from a normal model. We just happen to get a few big ones. Meh. All right, it has to be obvious. We're not splitting hairs here. This is fine. Met. Okay, and then, or a good old-fashioned dot plot. You could just plot your data from a sample on a dot plot. That looks, no outliers, no skew. It's symmetric. No skew, done. Move on with our lives. Okay, but it does require a picture. And that's pretty much the only differences between what we were doing before with proportions and now with means, okay? You might want to screenshot this one right here. The large counts as one big difference, okay? It's not just n times p, n times q. You might want to screenshot that. N is bigger than or equal to 30 is probably the most often one you will use, okay? Big sample sizes are always good. That's probably the most often. But if it is smaller than 30, then you have to draw a picture. Okay, and look, does it have a heavy skew or outliers? If it doesn't, done. It's all good, and that condition is met. 10% condition, same. Random condition, same as always. Nothing new there. This is new. Can you make the calculation? Can you type it into the calculator? That's new. But almost everything else will be the same. All right, ladies and gentlemen, we are out of time. Your video will sort of pick up from there, okay? We will practice all 4 methods next time, okay? So we're not moving on that quickly. We will practice all 4 pieces. The state, plan, do, conclude. We will do all 4. Yes, Michelle, I will push them out, and they will be in your OneNote. You don't have a Unit 7 folder yet, but I will make one for you. And so, yeah, I'll push these out in the next few minutes. Have a good one, everybody. Enjoy your weekend. See you, Tuesday.
Thanks, Wolf. Have a good weekend.
Thank you. You too. I should do that right now, shouldn't I? Let's see. How do I do that again? Class notebook. Distribute, new section, Unit 7.